staying till the end of the conference today. It has been a long one, but it's been a lot of really interesting topics, a nice segue into hardware again, and I want to get a quick read on people. How many of you guys have soldered your own PCBA or put components together, built a board, something like that? That's a lot more than I was expecting, actually. Almost everyone raised their hands here. How many of you have done that at a production scale, where you're actually working with a company to do a lot of boards at once? That's what I was expecting to see. So I'm hoping this will be interesting for you guys. This is kind of a topic that a lot of companies like to keep pretty secret. My name's Ryan Summers. If you can't tell by the accent and the name, I come all the way from Dresden. It's about 90 minutes south of here. That joke would have landed better if I didn't tell half of you about that already, but anyways. So I want to kind of walk us through the process of what it looks like when we're building kind of something from the ground up. And my background is all in safety critical systems. I've been an embedded engineer for 9 years at this point. I've done about 5 or so years of Rust, I believe. And most of it, even today, is C, and I've done C++ in the past as well. A lot of my projects tend to be safety critical medical devices, neurostimulators, surgical robots, things like that. The Rust stuff has not been in the safety critical realm yet. I've been talking a lot with Ferris Systems about that as well. And so if you have been paying attention to the slide here, we're going to go through and look at what it would take, for example, to make a Bluetooth pacemaker and kind of walk through the production process of that. And if you've looked closely at that picture, you might notice that we have a very interesting choice of battery power in this device. We've substituted the lithium for plutonium. And this is a real thing. This is an image that they give to clinicians so that when people die with these, they can properly dispose of them and send them to Los Alamos labs. So if you don't get anything else from this talk, know that at some point, someone built a plutonium-powered pacemaker for people to put in their bodies. And I think that is fascinating. Anyways, from a production perspective, what you're looking at with hardware generally is you're going to have your PCB. We had a nice introduction to this from James yesterday at the end of the day. You get your circuit board, you get your components, you put them all together, and it usually works. The problem is when you start building hundreds or thousands of them, eventually it doesn't. And for safety critical systems like this, like a pacemaker, you really need to know when it doesn't work. When we're going through the building process as well, there's oftentimes things that we need to do specifically, like we're going to need to give this thing a Bluetooth address if it's going to be talking over Bluetooth to the patient. It might need to have a specific serial number assigned so we can track the unit after it goes into someone. We're going to need to do lots of kind of calibration on it to make sure that we're measuring the heart rate properly and we can get everything working as it's supposed to and operating within spec. We're obviously going to need to do lots of testing on this device before we give it to someone to have it surgically implanted inside of them, because we don't get a do-over if that goes wrong. So the first thing I kind of want to talk about from a manufacturing perspective is what we call device provisioning, where you're going to find a serial number, put that in, figure out how to assign it to the device. Usually you start thinking about this pretty early on in your firmware development process. So I really want to try and leverage the C++, C background, and kind of the Rust background and talk about how we can use the modern Rust tools to really change the traditional approach to this and simplify it. So here you can see a pretty standard approach. We've got our microcontroller, we've got a little external memory chip. Our external memory chip is going to store some calibration information for any kind of sensor readings we're doing. It's going to store some Bluetooth address, the serial number, and things like that. In the microcontroller, we're going to have stereotypically our firmware in there, probably a bootloader and some other stuff. So what we're going to do when we first get this thing built, we're going to get our hardware, finally have it in our hand, and we're going to say, OK, it's not doing anything. What do I need to do? I need to program it. So the process generally looks like put the program on the microcontroller, have your computer kind of talk to it, figure out what serial number it's supposed to have. Maybe you scan a barcode or something like that. Send it down to the microcontroller, and it's going to store it in its memory somewhere. There's a few things here worth noting. There's some communication happening to the microcontroller. There's this external EEPROM chip, and there's a few things that kind of pay attention to. The next thing that I kind of want to bring up, and really I think is the crux of what makes this all possible, is the Probe.rs library. And we got a little bit of an introduction to it during James's talk yesterday. But essentially what it is just a method to program and control the flash. But it's a little bit different. Historically, we've had chip vendors give us binaries that are usually like, you buy an STM32, an ST-Link, and they give you a CLI with an EXE. And you say, OK, I can program binary, I can erase the chip, and I can do some of these things, but you can't really finally control exactly what's happening on the chip. And that's really where Probe.rs is kind of a new approach. It's both that binary that you can use, but it's also a library that you can use to finally control exactly what's happening. So you can do memory address level manipulation of the device memory to kind of tailor it to exactly what you want it to be. And that can really, in the manufacturing process, present some really interesting approaches. The other thing that you can do, because you have this fine memory control, is use the probe as a direct communication link. And so when I was talking about this kind of talking to the microcontroller during the provisioning process, you can sidestep that entirely by just using the probe. And so you can kind of cut down on the actual firmware that you need to develop. So if we kind of reimagine what we were looking at earlier with this understanding that Probe.rs can kind of enable us to do things that we didn't expect, the system diagrams start looking a lot simpler. We can completely eliminate an external memory chip because we can figure out exactly what those settings are when we want to program the chip itself. Because we can take Probe.rs, take our bootloader, take our firmware, create a settings block in Flash, and I'll put that directly onto the microcontroller as a single blob. And so you don't have to have a lot of the system components that we needed previously. You don't have a driver to talk to the EEPROM. You've reduced your cost of goods on the actual board. You don't need to talk to the microcontroller anymore. You're not sending a serial number or anything like that. And so really, this kind of approach drastically reduces the complexity of the design. And this is getting a little bit more towards what James talked about. The other process with hardware is that you need to deal with the eventuality that something will break. And if you talk to anyone that's built hardware, you'll realize that it breaks in very unpredictable ways. For example, this is a little circuit board that I made probably 5 years ago now, I believe. And it was a little kind of battery simulator trying to replace some test equipment that was super expensive for a client of mine. Didn't end up using this, but it was kind of my introductory Rust project. And it's open sourced on GitHub if you ever want to take a look, but it's entirely abandoned at this point. But the key things I want to point out here is on the left, you can see kind of the layout of it. And on the right, you can see all of the soldered components. And you can see that they're just absolutely minuscule pins. And James really talked about this when he was talking about the MOSFETs. I did surprisingly manage to get this with a hot air gun. And it took many, many tries. And I'm definitely stealing the hot sand idea that James had. But the key is when you get any kind of defect, like if one of those two little pins, which are like 0.1 millimeters apart, happen to bridge across to each other, you can really get kind of three eventualities there. It either just doesn't turn on, it does turn on, and it doesn't work, or it works just fine until it doesn't. And all of those things are kind of important aspects, especially when we're looking at some kind of medical device where it needs to be inside of someone, and we're not going to have the capability to replace it. So that's why we generally will employ a process of manufacturing test when we're building a lot of devices, where we're going to take it, we're going to put firmware on it, we're going to run it through the ringer and figure out if everything's working. The goal of these tests generally is to take the board and make sure that there's no hardware defects on it. This isn't that we're looking at the firmware itself to make sure it's functional. We're purely trying to see if there's been any kind of shorts or breaks. I've seen boards that got shipped to us that had a capacitor right on the very edge of the board. And during shipping, someone closed the box and just chipped the capacitor right off. And you would never see it because, as James said, there's capacitors on there that are about the size of like 1/10 of a grain of rice. And you don't notice that. And if that's critical to your application, suddenly things don't work and you don't know. So there's really 3 kind of tests that I've seen performed in the industry. The most simplistic one is someone will pay a technician to go and sit there, go through hundreds of boards, take a multimeter, measure something, write it down on a spreadsheet, continue, do that. And I've read a number of spreadsheets where technician wrote the number wrong, or then says like 3.5 volts, yeah, that's definitely greater than 3.8. And just passing units that they're not supposed to and things like that. So it can get a little bit finicky, and so because of that, a lot of times companies will try and move towards automated test systems. It ends up being a lot more expensive, but you can get a lot more bang for your buck, especially if you're going through kind of more safety-critical systems like a medical device. There's also this approach called a built-in self-test, and this would be like where the firmware first boots up. It'll take a look at all its peripherals, try and read through all the chips, just make sure there's some sign of life that it can talk to them and do the best it can. A common one that I've done for one of my clients is they have some external fans. First thing they do on boot up, spin all the fans up to max speed, check the RPMs. Are they spinning? We're good. So you can kind of work around it like that. And so there's an interesting mix. And this picture on the right is some hardware in my office of one of the projects I'm currently working on. And you can see this is very similar to a setup that you would see for what you would use for an automated manufacturing test, where you've got these pogo pins that hit onto a fixture on the right, and they'll make contact with the PCB on the left. The problem is that PCB is probably like about the size of a euro or a quarter. It's just absolutely minuscule. But often you'll see these kind of clamp-like devices where they'll sit down, break out all the electrical contacts out to some kind of connector, and then you'll be able to hook up automated test systems like benchtop DMMs, power supplies, and the like to actually do the testing process. So this is another example of a fully automated test system that I have sitting in my office. You can see lots of benchtop equipment kind of sitting there, all connected up to the box on the right where you've got the actual units that are being tested continuously. Lots of cabling, and then lots of PC USB control on the top left there. And that really kind of hits down at the cost of fully automating things can be quite high, but you can get a lot of value out of them. But when you look at a traditional manufacturing test, what you're trying to do is put in some kind of input into the device, maybe send it some commands, and then measure some kind of output to make sure the device is responding to that correctly. And like I mentioned, you want to try and systematically go through your hardware, understand exactly what things are happening, and test each one of the interfaces that you possibly can. And so this traditional approach has some downsides because you have to, again, try and talk to the chip. And so there's an interesting approach you can use with Probe.rs where you can use the probe as a mechanism to directly interact with it and kind of control the behavior of it while it's running. And so if any of you have ever used Probe.rs, you know there's probably a few ways that you can use it for debugging. Like semi-hosting is often one of the first hello worlds and embedded, where you just want to get some output from the chip. That ends up being a mechanism that you can use to kind of facilitate any kind of general I/O while you're running. ITM is a core site peripheral in ARM chips. Semi-hosting is also an ARM-specific thing. Probe.rs is mostly ARM-based. But ITM has the downside of it being a single directional kind of flow of information. It's only possible for the microcontroller to send data through ITM to the PC and not really in the other direction. The other most interesting approach here, and I talked about this a little bit at the beginning, is called RTT, which was coined back in 2013, I believe, by Seger. And the gist of it, it means real-time transfer. It's essentially just a ring buffer that is allocated in the microcontroller RAM memory at runtime that both the probe and the microcontroller can access simultaneously. And so it basically gives you a real-time I/O interface with your microcontroller as long as the debug port is plugged into it. And that's way more useful than you would expect, because suddenly you can transform your microcontroller that's this embedded device and make it behave a lot more like a standard desktop application because you now have standard in and standard out. From a manufacturing test perspective, this changes the game a little bit because you no longer need to write the firmware that handles the interface between the PC. You don't need to maintain any kind of interface documentation. The only way you're doing this is you have these little strings. You can just say, hey, measure the battery for me, and you can do just string formatting and get the voltage out of it. And so you can kind of collect all your information like that without having to write all this complex code to do it for you. So that's kind of what I wanted to talk about, is looking at how Probe.rs fundamentally changes how we can look at the manufacturing process because it takes a different approach to something like OpenOCD or the ST links. Because you now have this very, very fine-toothed comb when you're going through a manufacturing process. When you're going to program the firmware, you can custom tailor these binaries for each individual target as you program it. So say you have your first PCB come in, you can create a custom binary just for that PCB, program it on, move on to the next one, get the next one, and give each one of those their own individual binaries with their own individual settings programmed on. So it's kind of a different approach, and oftentimes you don't see a lot of the software perspective in manufacturing because they're just trying to use the tools that R&D has given them and move on with their lives and start shipping units. But there's a lot of interesting software design processes that we can look at and kind of take a higher level systems engineering perspective and simplify things. Being able to use that communication interface really reduces how much complexity you're programming, and that's kind of the gist of it. It should make things simpler and make it easier for you guys to start shipping hardware. There's a few other really interesting topics that you can look at when I was talking about kind of building the settings into the actual binary itself. Have any of you heard of sequential storage from the folks at Tweed Golf? James has. It's a wonderful crate that essentially lets you store data into the flash of the microcontroller as kind of tag length value-like settings. And so what you could do is build that buffer into your binary while you're provisioning the board, flash it on there, and then if you wanted to, at runtime, you can then append onto that list, add new settings, add new values, whatnot, as you need to. And so it kind of lets you start with something when you need to and automatically provision the hardware and then extend it in the future as you need. There's also a lot of other uses of Probe.rs outside of just the manufacturing use case. I know I was reading through some repositories like 2 days ago, and there's something called embedded test now, where you can run your unit tests in Probe.rs for all of your embedded software directly on target and go through it. That's super exciting from a medical device perspective because we're doing lots of testing. And another aspect is you can use Probe.rs for tracing, for using core site peripherals and looking at exactly profiling what your application is doing, especially for those timing and safety critical kind of use cases. The next thing I want to talk about is that Noah, the founder of Probe.rs, and I have been working on a project called forged.dev, and it's intended to kind of facilitate this process of customizing and building the binaries for you if you're trying to do this manufacturing process at scale. So if you're looking to kind of put firmware, bootloaders, application firmware onto your chips, you want to assign serial numbers, and you want to record all of that data in the cloud, definitely come and talk to me after this. We're looking for kind of like anyone who's doing production volume stuff. We handle design requirements enforcement, all device configuration, and everything gets stored for you, especially for those safety critical systems where you may need to conform with FDA regulations in the US or kind of keep any kind of quality around that. Other than that, that's all I have for you. I think I've got a little extra time, so I'm letting you all off early. Thank you very much.
Maybe we'll do questions before everyone.
Yep.
So does anyone have a question for Ryan? Anyone? Oh, Astada.
So I listen about everything about don't break the capacitor and you need to test on actual hardware. And yes, I'm completely with you. Is there a way to test on simulated hardware? Because you talked about embedded test, but I didn't catch all of it. Or any other tool to test on simulated hardware?
Testing on simulated hardware gets hard because you start looking at things like QEMU, and they've never been quite perfect at kind of emulating exactly what it is. And so it can work from a development perspective when you're trying to just like, I want to verify the functionality of my code, but manufacturing test isn't really looking to do that. Manufacturing test is trying to figure out, are there defects in the thing that we just created and whatnot? And so simulation doesn't help as much there. Does that make sense? Or? And what? Manufacturing test? Embassy test? I don't know. I've never... I'm not... What? Sorry? Embedded test. Gotcha. That's directly... It's part of the Probe.rs project, and I believe the entire idea is that you can run Probe.rs test, and it'll just run all your unit tests on the actual hardware target. So I don't know how well developed it is. I was looking at it and it looks pretty fresh. It looks like some of the commits came about a month ago or so, but definitely something to watch out for.
We have one over here.
Yeah, thank you a lot for the talk. I know we have a colleague who's looking into using Probe.rs with a chip where you explicitly use both cores and then logging and so on. Have you had experience with that?
There's been a lot of discussion about multi-core stuff, especially with the RP2040, and I believe there's been support being added for it. I know James might be a better one to ask about that. I haven't done much with multi-core stuff, and I know there's been some PRs landing recently for it. It kind of depends. If you're using it for debugging, that may be a more complicated experience, but if it's able to flash it, yeah, it has no problems with that.
Okay. Yeah, thanks.
And one more here.
So how much does this process differ from what's happening at very large scales? Is this something that is Probe.rs being used at like, you know, high volume production, manufacturing plants or anything like this?
It's a really interesting question because there's kind of different categories of manufacturers that care to different extents about the quality of their hardware, because there's definitely a mass consumer market where they're just going to produce as many things as they can. They're going to maybe quality control 1% of them just to make sure things are going well, and then just ship them. And if someone has a fault, they just return it and get a new one. And there's definitely some of that. And I know Noah's mentioned to me that people have contacted him about doing like large arrays of 200 programmers in giant panels of PCBs to do kind of simultaneous programming. There's also approaches where you can buy chips from vendors where the flash is pre-programmed with whatever you give them. It usually ends up being like kind of an initial bootstrapping stage because firmware teams end up developing the firmware further after that. And they're like, well, that one sucks now, and we want to put a new one on there. So it ends up often being a moot point unless you're very at the tail end of product development. And then finally, there's this kind of brand of contract manufacturer where you give them a giant sack of cash and they will give you a process that has 99.99% reliability. And so they're essentially figuring out exactly what they can over months of time, how to produce perfect boards without any issue. Because there's all kinds of weird things that can happen when you're like putting a board through the oven. Like it may look perfectly fine, but you ran it at too cold of solder temperature and you've got a cold solder joint, and that'll come up in certain cases as like a 2 kilo ohm resistance. And if that's in a power path, suddenly your board just doesn't work. And so they'll kind of work through looking at the holistic, fix every single problem they have, keep the process extremely controlled, and they'll give you quality hardware. And you'll see that a lot in safety critical and medical devices. One more over there.
One more over here. Sorry.
Hi, thanks for the talk. This is not really around software, but it's more about inspecting the boards. Are you, I've had a board made, and the only, one of the things that they offered was to x-ray the board, but they didn't seem to x-ray it with the components on, they just x-rayed the traces for some reason. But even if they did x-ray the components, are you aware of something like a DIY kind of solution without having your own X-ray machine to inspect sort of BGA components and like maybe through ultrasound? I don't know.
Well, so the intent of an X-ray on a BGA is to ensure that each one of the little balls is not going to short with any of the ones next to it. And so when you're looking at that, if you want to try and avoid some kind of X-ray inspection, you would think about what possible shorts they could be. So for example, if you've got a power and a ground plane short, that's obviously going to be like pretty easy to detect in your final manufactured product, because when you plug in power, it's just going to draw way too much current. There's other things like maybe you have a power line connected to one of your GPIOs on a microcontroller and it holds it high or something like that, and you can probably detect that by driving the microcontroller output and then reading it back. So there's alternatives that you could use to very expensive methods like X-raying instead to kind of work around what they're trying to detect.
Great. Thank you so much, Ryan, for your talk.
Thanks.
And